Well, I would like to welcome you back because I know that you couldn't wait to start this video. And in the previous video, we kind of left off with the idea that we just don't get six-membered rings only with sugars. We said that these open chain sugars can be an open chain, and then they can swing around on themselves and make these rings. And depending on where the OH group goes when they make the ring, we can get two anomers. And that was the alpha anomer and the beta anomer. And we said that actually all three exist in solution when we make these sugars. And one might be in much higher concentration than the other two, but it doesn't matter. All three are there. So we get this whole dynamic of open chain, closed chain, and then the actual closed chain itself will open up, the OH group can switch, and then the chain can close back up. And this gives us mutarotation, especially when we concern ourselves with polarimetry and the way that it will rotate light optically, either positive or negative. Okay, the story though is that it's not just a six-carbon chain as far as the sugars go that can swing around and give us these wonderful rings. It can also be a five-carbon chain. That's perfectly okay as well. So what I want to start with, the other example, we started with glucose every time, and I want to start with a different sugar. Of course, glucose is not a five-carbon chain. That couldn't be one of my choices. I want to start with a five-carbon chain now, right? So this is five carbons, and let me just color those. Here's first carbon, there's second carbon, there's third carbon, there's fourth carbon, and here's fifth carbon. So we get these five carbon chains basically, and this structure, if you want to look that up into that chart, is one of those structures that you should know, however, and that's D-ribose. D-ribose has all of the OH groups to the right hand side. Okay, so D-ribose, the story with five carbon sugars is that they're very similar to six carbon sugars. These five carbon and six carbon sugars, they are long enough to basically be involved in a ring structure, and that is very nice because we get some stability when it comes to the ring itself. So the story here is really no difference, except for the fact that it's still going to be this OH group that pairs up with this carbonyl group, and this is where the hookup occurs. So we don't really get a six-membered ring this time around. Instead, we get a five-membered ring. And the way that we draw that five-membered ring is that we show this carbon that was involved in the double bond now. Well, that gets paired up to an oxygen, and we see a five-membered ring that shows up. So this OH, this oxygen here, I'm going to draw purple. Well, that's this oxygen here. Okay, so there's the hookup spot. We get a five-membered ring. It's not as stable as a six-membered ring, but five-membered rings are okay. The molecules are happy with those. Cyclopentane rings are very common, right? So we've got to kind of fill in the remaining information here, just like we did with the story with glucose. When we make this ring, these OH groups are important because all of these are chiral carbons. So do they go up or do they go down? That's one of the things that we've got to look at. The same thing is going to happen up here at the top. This is an aldehyde functional group, and when that C double bond O breaks, what we are left with here is not a C double bond O now, but a COH bond. So does that point up or does that point down? The actual descriptions and the theories of those, they're all the same. So this is kind of the general template here that we've drawn, and I just really want to go through that general template and now talk about really the proper way that we should be drawing ribose as far as it's concerned with the actual Haworth projection. So I'm not even going to draw the carbon there. I'm just going to draw a five-membered ring, 1, 2, 3, 4, and the oxygen is 5. This was our aldehyde, so I've got a choice. The OH group can go down here at this location, or I'll just draw the five-membered ring again, and the OH can go up at that location. So there's really the dividing line between the two choices when it comes to the ring structure. Now, just like before, there's no difference. If the OH points down, it's one version. If it points up, it's another version. So there's really no difference there at all. If it points down, just like before, it's going to be the alpha version. And if it points up, just like before, at that anomeric carbon, that is going to be our beta version. So this is how we distinguish between alpha and beta. There's no difference as far as 5-membered and 6-membered rings go. The location of the OH group will tell you if it's alpha or beta. Now, what about these other OH groups? What do we do there? Well, it's the same kind of story. We said that if the OH groups here are on the right hand side, that means in the ring structure they need to point down, right? The same thing holds true for 5-membered rings. Again, there's no difference. So let's just make these different colors so you can see where they're going. Here's the OH group on carbon number 2. Here's carbon number 2. So the OH group is going to go there. It points down because it's on the right hand side. The same thing is going to happen over here. This OH group is going to point down because it's on the right hand side. The next carbon, carbon 3, well, this is OH and that's on the right hand side. So here's carbon 3. So here's the OH group and that points down as well. So there's carbon 2 and carbon 3 involved. Carbon number 4, well, we've colored that oxygen purple, so this carbon number 4 right here, it doesn't have an OH group on it, right? And the problem is because that OH group was the linker. The OH group is what makes this a ring. So this oxygen right there, that purple one, that was the OH group on that carbon. The H has kind of went off, if you want to think of it that way. The oxygen has attached to the ring on the first carbon, and we have this hookup of a ring as far as the ring concerned. Now, mechanism, reaction-wise, the story's a little different. But if you want to think of it in the basics, and that's what we're doing in this class, it's just looking at the basics. That's kind of how you can think of it. And then we've got this 6-carbon chain, or this 5th carbon in the chain, and this is a CH2OH. And just like before, off of this 5th carbon, or 4th carbon, there's our 5th carbon with the OH group, and here's our 5th carbon with the OH group. So there's the transformation from the Fisher projection to the Haworth projection using a 5-carbon membered ring, 5-membered ring, instead of a 6-membered ring. So that's as easy as it gets. That's really all that we're after. If you want it to get fancy, and if you want it to maybe put a prettier spin on these structures, you are more than welcome to darken these in if you want, to let you know that these are kind of faced toward you. So the OH group is above and the OH group is below. Notice that this was D-ribose. So in the name down here, this structure, because this anomeric OH group is pointing down, this can be labeled as alpha D-ribose. And here the OH is pointed up, so this can be beta D-ribose. Right? So the naming system is the same, the anomeric system is the same, the Haworth, as far as how it relates to the Fisher projection with the position of the OH groups, are the same. It's all identical. The only difference is this 5-membered ring instead of a 6-membered ring. And again, I'm saying 5 members. That's because oxygen counts as one of those. So here's my first member, second, third, fourth, and 5th. There are 5 atoms that make up the ring, so 5-membered ring. Now we've got some special terms that we need to throw out here. Now that we've talked about a 6-member ring and a 5-member ring, we have some terms that we would like to maybe throw out to get you used to them. And if these rings are 6-membered and 5-membered, they have certain names that they go by. In a 6-membered ring, and now these are specifically for sugars. In a 6-membered sugar ring, we call these things Furanose. So these are Furanoses, right? So a six-membered ring, if I didn't want to say six-membered ring every single time, it's kind of a tongue twister. Try to say that 3 times fast. You can say Furanose, and we should understand that this is, okay, a six-membered ring, and there's an oxygen there, and these carbons involved in the ring, they have multiple OHs all the way around. So that is a six-membered sugar ring, is a Furanose. What does a five-membered sugar ring go by? Well, a five-membered sugar ring doesn't go by Furanose, of course. It goes by Furanose. So Furanose and Furanose. So it makes your tongue sound kind of sexy when you say it. So say it really, really slow and say it over and over and over, and hopefully you'll get comfortable with the idea that we are working with Furanose and Furanose sugars. So five-membered and six-membered rings, that is what they go by. The name comes, of course, from Pyran and Furan, which basically is related to some old terminology that kind of means 5 and 6, and it brings in the whole word of cyclic ethers and the stem and the root and the history of these names go back pretty far. But Pyranos and Furanose, that is what we call them nowadays. If you want to know what the structure of Pyran looks like, well, Pyran is this six-membered ring with an oxygen in it, and there's a double bond here and here. This is what we call Pyran, and this is where Pyranose comes from. So you see a very similar structure here as far as the carbohydrate is concerned. Of course, we don't have the double bonds in the ring, and there's no OH groups on this ring, so we can't call it Pyran. So that's why they modify the name up a little bit and call it Pyranose, because we're talking about a carbohydrate. The Furanose comes from the old term of furan, and that's basically this five-membered ring structure, and there's 2 double bonds on it as well. So that is furan, F-U-R-A-N. And if I take furan and get rid of the double bonds and put OH groups on that structure, then we change that into a furanose. So that is the definition of the sugar counterpart to these root names. So that's the story with a 5-membered ring. There's no difference in it than a 6-membered ring. They're exactly the same. They have the anomeric carbons there. They've got the alphas and the betas, just like before, and the whole relationship with how it goes and couples with the Fisher projection is identical as well. So have fun with converting these structures back and forth. There's going to be quite a bit of questions on the homework. There's going to be quite a bit of questions on the quizzes and the tests that concern it, just so that you can prove that you know how to convert between one structure to the next. Alright, so this is where we're going to stop as far as the structure is concerned. In the next video, we'll continue on with our discussion of carbohydrates and see what else maybe that we need to take away from this lecture.